In the last video, we looked at individual chemical bonds and discussed the nature of each of those based upon the difference in electronegativities of the two elements involved in the bond. But now what we're going to do is we're going to look at molecules that have more than one type of bond present, and we're going to try to rationalize the way that a molecule is going to be set up based upon a set of bonding rules. What we're going to do here is we're going to draw what's called Lewis structures or Lewis dot structures of compounds. Now, we've already seen Lewis structures for individual atoms. For example, we saw that hydrogen had a Lewis structure that looked like this, where that one dot there represents the single electron that's in the only valence, or actually the only orbital, around the hydrogen atom. But if you look at something like carbon, it looked like this, which had 4 electrons, 4 dots, representing the 4 electrons that are in the valence shell. Okay, only in the outermost shell of electrons, not what's inside the core, what's part of the closed shell, so to speak. Now, we've seen that compounds like hydrogen are going to form via covalent bonds due to a mutual attraction for the electrons from each individual hydrogen atom. And it seems kind of straightforward that it would work out this way, that we would be able to get hydrogen to have its full complement of electrons, 2 electrons that is, while forming a bond that is represented by those 2 dots, the sharing of those 2 electrons. And in fact, every individual bond is composed of, well, I gotta say that carefully, there are some exceptions, but for the most part, every chemical bond is composed of 2 electrons being shared by 2 atoms. Now, what about more complicated molecules? So for example, what if instead of something simple like H2, we wanted to understand the bonding in NH3? Okay, well, we can still kind of take sort of a simplified approach here. We know that nitrogen is going to have 5 valence electrons. And by the way that we've drawn it, and we discussed this in the previous video, 2 of those electrons are going to be paired up and 3 of them are unpaired. Okay, and we're going to have hydrogens. Each hydrogen is going to have 1 valence electron. Okay, so you can, I think, put together that the molecule is going to look something like this when we're done. Okay, what's the significance of this? Well, I think it's more significant to recognize what the molecule is not. The molecule is not a hydrogen atom stuck to a hydrogen atom, stuck to a nitrogen, stuck to a hydrogen. It's not 3 hydrogens stuck together. Okay, neither one of these is correct. Okay, so this does give us somewhat of a picture of what the molecule looks like. It's a central nitrogen that has 3 bonds, each one going to a different hydrogen, and, very importantly, there's a lone pair of electrons. And you'll see later on, if you take organic chemistry, that the lone pair of electrons is crucial to the reactivities of a lot of different compounds. Okay, but molecules can get even more complicated than this, so it would be nice if we had kind of a systematic approach to drawing Lewis structures. So we're going to do that right now with a compound that's fairly straightforward. Okay, one that you probably could even piece together on your own, but this will serve as a good template for us to build our procedure on. Okay, so the first step in drawing any Lewis structure is to find the total number of valence electrons in the molecule. Okay, that means looking at each atom and figuring out how many electrons in the valence shell are being brought by each atom. So here we have a carbon, which we know is going to have 4 valence electrons. It's in group 14. And we have hydrogen, which is going to bring 1. But we have a total of 4 of these hydrogens. Okay, so altogether, the molecule that we draw is going to have 8 valence electrons. Okay, so that's our first step. Second is to arrange the atoms to meet valency rules. Okay, so what do I mean by that? If you think back to the Lewis structures that we showed for the individual atoms, okay, we had boron, carbon, nitrogen, oxygen, and fluorine, and then neon. These were the representative elements. Okay, we said that the number of unpaired electrons was going to be equal to the normal valency of that element. So boron has 3 unpaired electrons, so we would expect it to form 3 bonds. Carbon has 4, so it would form 4 bonds. Nitrogen has 5 electrons total, but only 3 unpaired. So that should be trivalent, 3 bonds. Oxygen has 2 unpaired electrons, so it's divalent. Okay, fluorine has 1, so it's monovalent. And neon has no unpaired electrons, and we know that neon, being a noble gas, doesn't form bonds. Okay, and we see this when we look at the structures. I mean, the boron's compound with hydrogen is BH3. Okay, carbon, its compound with hydrogen is CH4. Nitrogen is NH3. Water, well, oxygen is H2O. Fluorine is HF. Okay, so this shouldn't come as much of a surprise. So if we keep these valencies in mind, it helps us to arrange the atoms that are part of the molecule. So we have CH4. Okay, we know that what we don't have is a structure like this. Okay, and how do I know that? Well, for a couple of reasons. Number one, this hydrogen that I'm pointing to is bound to 2 different things. But hydrogen has 1 unpaired electron, so hydrogen is monovalent. It can only form 1 bond. So that by itself rules this out. In fact, any structure that involves hydrogen being bound to 2 or more things is going to be invalid. Okay, so what if I were to arrange it like this? Okay, by drawing it this way, I'm implying that each hydrogen is individually attached to the carbon. Okay. And then the third step is to simply distribute the valence electrons. And we want to distribute those valence electrons in a way that gives every atom its full complement of electrons. Okay, and that means, for the most part, we're going to follow the octet rule, which basically says most elements like to have 8 electrons. Well, most of the elements we're going to be looking at here are going to like to have 8 electrons. There's exceptions to that rule, of course. Furthermore, there are some elements, well, hydrogen, for example, only wants to have 2 electrons, so it has more or less a duet rule. But the general rule is the octet rule. All right, so here I have my carbon surrounded by the 4 hydrogens. Okay, I have 8 electrons that I need to account for. So I know that this hydrogen's bound to this carbon here. That means there must be 2 electrons there. If they weren't there, there wouldn't be a bond. There wouldn't be any point drawing the hydrogen next to it. So that takes us down to 6. Okay, the same thing goes here, takes us down to 4, here, down to 2, and here. Okay, so as you can see, we have accounted for all 8 electrons. Okay, and that means that we found a spot for them. It doesn't necessarily mean that we found the right spot. So what we want to do is look at the structure a little bit closer and make sure that everybody's seeing the right number of electrons. And we said hydrogen wants to have 2 electrons. I can look at each one of these and see that they both see, I'm sorry, all 4 of them can each see 2 electrons. So this hydrogen right here sees both the electron that it brings to the table as well as the electron that it's sharing with carbon. Carbon, on the other hand, is going to be seeing 2 electrons plus 2 plus 2 plus 2, a total of 4 electrons. I'm sorry, a total of 8 electrons, meaning that carbon has its octet, hydrogen has its duet, everybody's happy. Okay, so our final Lewis structure, I'll redraw because the other one got a little bit messed up. Looks like this. Now, if you get to this point and you choose to simplify the structure a little bit, you can by just using lines to connect the atoms. Okay. Let's try doing the same thing now with a molecule that looks a little bit different. Let's look at water. Okay. Again, a molecule you could probably figure out just by looking at the Lewis structures for the individual elements. Okay, but let's figure this out. And if you want, you could pause the video here now and try this out on your own. Okay, so what I'm going to do here is start off by counting up the number of valence electrons. Okay, we have hydrogen, which has 2 valence electrons. I'm sorry, let me restate that. Has 1 valence electron. And there are 2 hydrogen atoms, which gives us a total of 2 valence electrons from hydrogen. And we have oxygen. Each oxygen atom is going to have 6 valence electrons. Again, remember, 6 valence electrons because it's in group 16. And there's only 1 oxygen atom. So we get 6 valence electrons. And again, we have a total of 8 valence electrons. So the next step is for us to draw out the structure. Now there's 2 different ways you could have drawn this. You could have either arranged it so that you have hydrogen bound to hydrogen, which is then bound to oxygen, or hydrogen bound to oxygen, which is then bound to the other hydrogen. And I tend to think that most folks probably look at this and by their gut feeling believe that it's going to be the one on the right side, and it is. But you can't always be sure. You always got to make sure you look at the electrons and look at the valencies to make sure. But we know hydrogen wants to be monovalent, and here we have a hydrogen that is divalent. That's no good. Also, we have an oxygen here that appears to only be monovalent. We know it wants to be divalent. Okay, so that kind of rules this guy out. All right, so now let's look at these 8 valence electrons and start to distribute them. Okay, I like to start by putting the valence electrons, let's see here, I like to put the valence electrons in the spots where I'm already implying a bond by putting 2 atoms next to each other. Okay, so by drawing the hydrogen next to the oxygen, I'm saying there's a bond there, so I have to have 2 electrons there. So right off the bat, I'm down to 4 valence electrons. I also notice that each one of the hydrogens has its full complement of electrons. Each hydrogen sees 2. Okay, so there's not going to be a whole lot more that we're going to be able to do with them. Oxygen, on the other hand, only sees 4 electrons, and we know it wants an octet. Okay, so that means that the remaining 4 electrons have to be given to the oxygen. And this is the structure that we have for water. Okay, so we can see here that there's a bond between hydrogen and oxygen hydrogen, and we can see that the oxygen has a lone pair of electrons, or 2 lone pairs of electrons actually. Now, if we were to try to clean this up by just drawing lines for the bonds, you can do that. Okay, but you can't forget to draw in the lone pairs. Okay, so that's how we draw a simple Lewis structure. Okay, so let's look at something maybe a little bit more challenging. And let's look at an example where we don't only use single bonds. So let's consider a molecule of O2. Okay, now, just like before, you can pause the video and try it on your own if you like, but I'm going to start working on it here. We have a molecule of oxygen that has 2 oxygen atoms. Okay, so oxygen is going to have 6 valence electrons. Okay, there's two oxygen atoms for a total of 12 valence electrons. Okay, and that's it. And there's only one way that we can really arrange the atoms, and that's next to each other. Now, like I said before, one of the first things I like to do is to distribute the electrons, first of all, into places where I'm already implying that there's a bond. Okay, so that's my first 2 electrons. We're down to 10. We know that oxygen wants to be involved in 2 bonds, but as I've drawn it so far, there's only 1 bond. Okay, I also know that oxygen wants to have 8 electrons. Now, if I were to try to distribute these 10 electrons, let's do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What I find is that I've built a structure that has a full octet of electrons on one side, but not on the other. Okay, so this is not going to be a good Lewis structure. So we say it's not plausible. Okay, because one of the atoms does not have its octet. Okay, another way that we could have arranged them, okay, would be putting 2 between the oxygens, and then the other 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and here you can see that we have 2 structures that are not, I'm sorry, 2 atoms that do not have a full octet. Okay, so that's also not plausible. Okay, the only way that we can take care of the valency problem, which is that oxygen wants to have 2 bonds, and take care of the valency problem, or the valence electron problem, which is that we have not enough valence electrons, we can draw the molecule like this and have 4 electrons be shared between the 2 oxygen atoms. Okay, if I do that, then the other 8 electrons, we go 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'm going to draw this out using sticks here. Okay, here we can see both oxygens have the double bond, or both oxygens are involved in 2 bonds. Both oxygens can also see a total of 8 electrons. Okay, so we've met the right number of valence electrons, and we have the right valency. Okay, so double bonds are a possibility. Okay, you can try N2 on your own as well. Okay, but with nitrogen, okay, we have 5 valence electrons, and there's 2 of those atoms, so that's a total of 10 electrons. Okay, again, we only have one way to arrange the atoms. Now we know that nitrogen wants to have 3 bonds. Okay, we also know that each nitrogen wants to see a total of 8 electrons. We have 10 electrons, and we're going to start off by placing 2 of them, which takes us down to 8. And we can already see that if we try to distribute those 8 across the 2 nitrogens, we're going to wind up in an even worse situation than what we had with oxygen. Okay, but we're going to have a full octet on the nitrogen on the nitrogen on the left, but the one on the right is only going to have a total of 4 electrons that it can see. So we can fix this by putting in a triple bond. So that's a total of 6 electrons, which means that we have 4 remaining that we have to find spots for. Each nitrogen only sees 6, so they can accept another 2. And that's our Lewis structure. And we can tidy that up a bit. And that's what it looks like. Okay. Now we're going to split the video here, and in the next video you're going to see how we can deal with slightly more complicated situations, like when we have charged compounds, or if we have exceptions to the octet rule.